Hello everyone, November 24th. Alright, so yesterday we got stuck here and actually I tried to submit it and it didn't work. Timeout. I mean, the solution is correct. I mean, we went through a lot to get it to work. I mean, there's a certain amount of math involved, but no, it's okay. We can handle this. But what happens is, like, initially the goal is to check, like, because the problem is asking for like, we need to decide how many unique prime factors we need to have among these prime factors, right? So we can have 1 or 2 or 3 or all the way up to the prime factors, and then need to go through all of them to find out which one will produce the best results. And then I timed out. I mean, that's basically the solution I submitted. Even though we used this proof to compute it like very fast. That would be a very fast way to compute. But it's actually not that fast. Why? Because we have to do, I mean, that's actually not the solution that I submitted. That's just me trying to do some things. So yeah, this is the one we have, right? We have this part. And this turns out to be extremely difficult to compute for this value specifically. A plus 1 is 2, B plus 1 is 3, and K is 0, right? And then this one, we have a gigantic value. I think it's 100 and something million. That's really big. Right? So no, 10 million. It's really big. So it's impossible to compute this directly. So we have to, and it's not possible to do, like, say, like multiply it 1 by 1. It's also not possible because it just takes too long. So what I need to do, what this question is asking for, not just this part, okay, but also we need to write our custom power, okay? We need to write up custom power and put mod in it, so the number won't get too big. So basically that's how we're gonna approach it. So that, if we have time today, that's how I'm gonna approach it. And one more thing, right? One more thing. Here I'm doing like n equals 2 and all the way to basically half of prime factors. But I actually checked. So we can see, this is what I checked, right? So I basically put, this is the prime factors, and this is the n. Like, what is the optimal n for this, right? So like, how many prime factor we have to do. And it turns out, I don't have a proof, but it turns out 3. That whatever value we have, you just divide by 3 and then round it up, right? So all of this, you see, like 20, 20, 20, 21, 21, and then this one all the way goes to like these values. There's also 3. We have 3, and then we have 3. So I think that's actually what I'm trying to do here. You see, I did this thing, right? Divide by 3. Now, do I have a proof for that? I might be able to come up with a proof, but at the moment, no, I don't have a proof. All I have, actually, I mean, I don't have anything, honestly. But it's going to be this, right? It's going to be this. So we just need to prove it, that the, I mean, to have 3, what we actually have is A is going to be 2, right? Because n is this one divided by 3, and s is this one minus n, so this is going to be 2. Most likely 2. I haven't thought about the round situation. I mean, round, like I say, if prime factors are smaller, right, a smaller value divided by 3, and then round, it will actually round to a higher value. Then this a is actually might be 1. It is a possibility A is going to be 1. So no, I don't know. I just, based on all these factors, right, all these not rule patterns, I guess it's going to be just 3. but I don't have a proof. But anyway, so because it's always timeout, so I think what I can do is just write our own power function, and then, just call it that. And it is also possible, like if it's divisible, right? And you know what? Yeah, that's that. So I'm gonna try this, but let's finish today's challenge first. What is this? Sum of subarray minimums. Given an array of integer, find the sum of min b, where b ranges over every contiguous subarrays of, since the answer may be large when the mod it, all the subarray. Oh my god. All the subarray. Subarray. I mean, if I 3, 1, 2, 4, right? Subarray of 1 we have handled. Subarray of 2. And subarray of 3. You know what? What if I go say, because if you're 1, right, and all the subarray that includes you is going to be you, right? And for each value, the number of subarray that include you, I think is the number is set, right? The number is set. So including you, it's going to be how many? How many will include you? Be 1, 2, 3, 4, 5, 6. Or you can say like what subarray that does not include you. And for this one, 1, right? And we know the total number of subarrays is how many? It's a 2 to the 4 minus 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Actually, no, it's only 10. Oh, no, that's 1 plus 2 plus 3 plus 4. That's the subarray. So that's 10, right? So among the subarray, I say the one that including 1, we can say the one ending in 1, the one starting in 1, right? So the one ending in 1 is going to be, well, 1 by itself is 1, ending in 1, so that's 3, 1. Well, that's just 2. Start in 1 is going to be 1, 2, 1, 2, 4, right? So that's also 2. But what about the ones that contains 1? How do we compute that? All the subarray that include, well, it's the subarray that end in 1. Nah. Let me think. Hold on. So on the left hand side I have 1 value. On the right hand side I have 2. So if I want to take something on the left, something on the right, it could also be 0. So I'd say on the left will be 3 or nothing. On the right it can be 2, 2, 4, or nothing, right? So I can pick 3 and nothing, right? 3, 2, 3, 2, 4. So that's 1, 2, 1, 2, 3. That's 2 times 3. That's going to be 6. Do we have 6? 1, 2, 3, 4, 5, 6. Yes. We have 6. That will include 1. Okay. So once that is done, we can go look for the second smallest. That's 2. So we want to find all the ones that include 2 but does not include 1. How do we do that? Well, we can find holy crap. We need to find the position, right? So we have 2 and I need to go all the way to 1, right? So as long as I don't cross, I don't go beyond 1, then 2 is the smallest, right? So I just don't go beyond 1. So I need to know 2's index and 1's index and make sure that they don't go beyond. If I go beyond, that can be 1. So for 2, what we have is empty and 4. So that's on the left is empty, on the right is empty and 4. So we have 1 times 2 equals 2. So for 2, we have 2. That's correct. For 3, we have empty on the left and empty on the right. So that's 1 plus 1. That's 1. So 3 is 1. For 4, it's also 1. 1 plus 1. So the result is 6 times 1 plus 2 times 2 plus 3 plus 4, which is 6 plus 4 plus 3 plus 4, 17. Okay. So what we can do is rewrite this, put the index in, okay? And then how are we going to identify where we extend? I mean, the first one is easy, right? Then we have the smallest, we have that index, okay? The second one comes, doesn't matter if it's smaller or larger, I have the index. So I have 2 index now, okay? And the third one comes. So the third one comes. How do I know where I put it? That's a good question. How do I know where I put the third one? Because it cannot go beyond. So I have the third one, and I need to know where do I belong in this? Third one comes, so I know its position, okay? I know its position, and I know the previous position, but I cannot go beyond. Yeah, how do I know where should I belong? It just means I have the previous indices. Now the new index comes out. I want to know where I belong. Where do I belong? Where do I belong? Let me think again. 3. Okay. And then we comes 1. So 1 is smaller. So 3, I can do 3. I'm thinking about monotonic array. Then 2 comes. 2 is bigger. And okay, 2 is bigger. So I just put it there. and 4 is bigger, and I put it there. And once we're done, because if I have something that's smaller and I want to pop, then okay, that makes sense. Unless we have something bigger. So once we're done, then we go from right to left. We go from right to left. Then we don't have. I think monotonic array will work. Right? We can use this as an example for monotonic array. So we have 11, 0. Okay. Now we have 81, 1. Because 81 is smaller, we want monotonic increasing. So 81 comes in, I will pop. Oh no, my bad. We don't pop because 81 is bigger. That's good. 94 comes in, we don't pop. 43 comes in, okay? 43 comes in, though 94 need to be popped. And then pop, I know to my left on the monotonic array is the one that's smaller than me. So I cannot reach there. And to the right, there's also something smaller than me, so I cannot reach there. So this position is 2. To the right is 1. So on the left, we have 2 minus 1. That's 1. On the right is going to be 3 minus 2 is 1. So it's going to be 1 times 1 times 94. So this one get popped. Now we'll go to 81. All right, 81 is also going to get popped because 81 is larger than 43. So we have 81 to the left is going to be 1 times 81 to the right is going to be 3 minus 1 is 2, right? Yes. So 1 times 2 times 81. So 81 get popped. 11 we don't pop, so 43 is there. Now the last one, 3 comes in, 3 and 4. And if it's not 3, if it's something bigger, then we just produce the monotonic array, and then we can handle it from right to left, which just on the right is going to be the total length, right, minus that. Because I mean, for 11 on the right is going to be 1, 2, 3, 4, 5, because it could be empty, so it could be 5, which is 1, 2, 3, 4, 5. 5 minus, yes. So now 3 comes in. We'll pop 43 first. So 43 will be 3 minus 0 on the left. So 3 times 1 times 43. So that's popped. And then 11 gets popped as well. Right? 11 gets popped. 11, the left is going to be 1. So the left has to be a minus 1. So it'll be 1 times on the right. That's 4. 4 minus 0. That's 4. 1 times 4 times 11. So 11 gets popped. So finally we got 3, 4. Right? And then when we handle 3, 4, we put 3, 4 there. And then we say on the left, because there's nothing on the left, so we have to do minus 1. So we say minus 1. Basically 4 minus 1 is 5. Right? Because we have 1, 2, 3, 4, and empty. So it's 5. Times on the right is going to be the total length is 5. Minus 4 is 1 times 3. So all we need is check if this is correct. Hold on. So we check is 1 times 94 plus 2 times 81 plus 3 times 43 plus 4 times 11 plus 5 times 3. Is that 444? That is 444. So we have this. Basically, we solved it. Oh, by the way, I also figured out what went wrong yesterday. Yeah, basically, last night I'm having a lot of issue with my terminal, and the reason was I installed Homebrew, right? I installed Homebrew, but it was using the ARM, the M1 chip, the M1 chip Homebrew. Now the M1 chip Homebrew is different from the non-M1, the Intel. homebrew. The M1 chip homebrew installs everything under opt/homebrew directory. But the Intel installs that, I think it's opt/ or is it user local opt? Maybe that. They're installed in different locations. And I had used homebrew before on this laptop when I set it up without M1 chip. So everything was, all the links, all the sim links, everything is pointing to the num M1 chip. So when I accidentally deleted homebrew and reinstalled it under M1 chip, the two they don't work together. So the solution yesterday was just uninstall everything again and then set all my terminals to Rosetta, and then I installed homebrew again, and now it's installed in the right directory. It was, I don't say total mess, but it was not it's not a good experience. I don't recommend it, but it's done. All right, so we're gonna have a stack, okay? Then we just say for I, A in enumerate array, if, no, while stack and stack -1, 0, if this one is larger, what would it be equal to? Holy crap, equal to. Have you think about equal to? What's the equal to situation? Equal to, damn. Equal to. If the two values equal to, then this can take this. I think it'll be the same. I can pop if it's equal to. I think equal to will be fine. I can pop equal to, it's okay. Especially if, because all these are bigger, right? And now something is equal to, so I just say from this to this. But it's okay, I can just say from this to this as well. I don't know, maybe we should do it equal to just to see if our thing works. Let's say, how about this? Okay, so in my mind, we'll go 3, 0, right? And then 1, 1 comes in, 3, 0 pop out. We have 1 times 1 times 3, right? And then 2 comes in, and then 1, 3. So 2 to get popped. So that's 1 times 1 times 2. And now I have 1, 1 and 1, 1. And I say I pop you as well. So I pop this 1, 1. When I pop the first 1, 1, on the left we have 2 times 2 times 1. And eventually we have 1, 3. And when we have 1, 3, what we're going to do is go for the left. So that's 4 times 1 times 1. So we have a 3 plus 2 plus 4 plus 4. Was that 13? Let's see if it's 13. Hold on, I need to deal with my cat. They're not being good. My cat is always hungry. 13, so it works. So I can say, actually I need to put something in there. What do we put in there? We need to put put it has to be of extremely small value. So all the value are positive. So I can just put, I can put 0 in there. I can put 0 and -1. All right. And then we say if this is smaller, no, larger or equal, larger or equal to A, then we're gonna pop it. Okay. So we're gonna pop it. When you're gonna pop it, we're gonna have a result. Okay, result equals 0. How do we pop it? We're gonna pop the index. No, v index equals stack.pop. Okay, and then we say rest plus equal to index minus stack minus 1, 1. That's the left side times the right side. Can be I minus v. No, I minus index. Right, so this and then times v. And of course, we're gonna mod this. Okay, we're gonna mod this. And then we're gonna come back, try it again, try it again, try it again, try it again, until we cannot try, then stack.append AI. Okay, so once we're done, then we're gonna go from back to front, right? Back to front. We're gonna just pop, right? And each time we pop, and then we say while stack v index equals stack.pop. But we cannot pop the first one. So while length stack is larger than 1, cannot pop the first one. So we pop this in the rest plus equal to. That's the same thing. We can just copy and paste this and then change one thing. Okay, change one thing, which I'll have to put it here. N equals len array. What do I change? Index minus, this is fine. This is I, there's no I, so here is going to be n minus index times v, right? And then we'll return rest. All right. Let's try to see how this one works. We can definitely set up some test case for this. 444. Yeah, I don't know why my cat is always hungry. I mean, we feed them. I think we feed them enough. I don't know why they're still hungry. So let's work for these two. All right, let's throw some value at it. What do we want? 10. 10 test cases. Oopsie doozy. We need to say from random import randint, and then we're gonna say 10 test equals this for this in range. Let's go 10 again. Randint 1, 2, 3 times 10 to the 4th. Okay, and now I'm going to print test. Okay. Oh, I forgot. I have to exit. Yeah, this is the only thing. I don't know how to solve it. Okay, this one works. But I also want this to be small. 1 to 5. Okay, so the purpose is to create some repeats, which is also important. Okay, so with repeats, Oh, I was going to say we have issue, but no, there's no issue. Okay, so edge case, singles. Still works. I think we should be good. All right, let's try this. It's a new problem. We got a wrong answer. That is not expected. Did I not mod it enough? That is unbelievable. I thought I have. I mod everything. Ooh, maybe. That should be res plus this times this. Yeah, maybe. Yep, it's a mod issue. It's a mod issue. There we go. Oh, should do pretty well. Yeah, we identify the trick. That's why we got this one. Okay, 907. So, the key is to, well, I shouldn't say the key. We can say, we can pick, right? We can pick any number in array and ask the question, how many subarrays that include this number also have this number as its smallest value. Now the answer is that we can put this number in the middle and extend left and right words until we hit some value that is smaller than this number. Then the maximum extension on the left and right are the range where the current number is the smallest in in all the subarrays that include it. Now say, now given the example, right, 3, 1, 2, 4. For number 1, we have one value to its left and two values to its right that are all smaller than it. Now the total number of subarrays, right, that include 1 can be thought of as the number of choices on the left multiplied by the number of choices on the right. Now, the choices on the left is 1 plus 1 equals 2 because we can pick 3 or pick nothing, right? The number of choices on the right is 2 plus 1 equals 3 because we can choose 2. Actually, we should just say 2, 2, 4, or this. Now we have to this, or pick it's not really nothing. Yeah? Let's pick this. Thus, the total number of subarrays that include 1 is 2 times 3 equals 6. All of them and the sum of these subarrays is 6 times 1 equals 1 equals 6. Similarly, we can perform the same trick for the other values. Now the question is, how can we identify, how do we find out the number of values to the left and right, values to the left and the right that are smaller than the current number? And the answer is monotonic increasing array. Each time we encounter a value that is smaller or equal to the top of the stack, it is guaranteed that the top of the stack is surrounded, right? Surround. How do you say surround? Surrounded on both sides by the immediate values that are smaller than it. Alright, if we include the indices in the array, it is trivial to find out the number of values smaller to the top of the array on its left and right. Okay, so the solution follows this logic. And we pre-populate the stack with 0 minus 1 to simplify the computation. So there's ON, because everything is hit only once. Okay, now I can check the solution. Monotonic stack. Yeah. I just want to see. Yeah, look at this. Monotonic stack and dynamic programming. Why would you need dynamic programming? People are saying this should be hard. I mean, it does have two twists, right? It does have the two twists. So the first one is to figure out this, how to find the sum, and the second one is figure out using monotonic. Yeah, but I'll say it's getting close to hard. What is this DP solution? Previous smaller. Stack is empty, so no previous smaller element. Okay. Then 6 comes in. 8 push to the stack. Eight is removed. So no previous smaller element. So 6 is the smallest, so we'll add 6. And 6 is the smallest, and I have 2. Okay. 3 is smallest, so and in this is going to be 1, 2, 3. Okay. Now 5 comes in. 5. So I use the previous smaller because it's bigger. So I use the previous smaller to find what is 5 is going to do, like ending at 5, right? Ending at 5. Because everyone is trying to find all the thing that ending in this. Okay, so ending in 5. 5 by itself is going to be 5. And everything else is going to be 3. So it's just going to be the smallest, because it's all this, plus 5. So dpi equals dp the previous, and I minus the previous smallest times array I minus. Oh yes, I minus the previous. So it's, if I am 0, 1, 2, 3, so it'll be 3 minus 2. That's gonna be 1. All right. So yeah, so because the previous smallest, it's in the stack, and I have its value, right? I have its value, its value and its index. So now the current one comes in. If it's bigger, then I need to know the number of values in between, because all the values in between, because it's a monotonic array, right? So every value in between is going to be smaller than me. Wait, hold on. Every value in between is going to be smaller than me, because monotonic increasing, right? Yeah, so I will pop it until I cannot pop. So everything is going to be bigger than me, not smaller than me. It's going to be bigger than me. So it's going to be I minus previous smallest 2. So it's going to be 9 plus 5 for this. Okay, 4 comes in. Yeah, 5 I have to push. 4 comes in, I'll pop. Okay, so we pop this, but now we go to 3, right? So what we have is 3, which is 2, which is 9, plus 4 minus 2, which is 2. 2 times 4 is 8, so 8 plus 9 would be 17. Yes. 9 comes in, just push it in. But 4 we'll put 4 in here. So 9 comes in. Okay, how do we do 9 comes in? So I know 4, which is the value for everything ending at 4. So yeah, 9 comes in is the same. So 9 comes in will be 9 plus 17 will be 26, right? This will be 26. Yes. And then 2 comes in. 9 will push in. So 2 comes in, we'll pop everything, right? We'll pop everything. And once we pop everything, that just means I will use -1, actually. So it's going to be 6, 7. 2 times 7 be 14. Yeah, pop, pop, pop. And, oh yeah, and just +1, that'd be 17. Not 17, 2 times 7, 14. Jeez, come on. And you add everything together. Yeah, some more. I don't know if I like it. I like this. This seems more, I mean, the DP seems to be working a little bit. Poner las 3 pies del gato, right? Buscar las 3 pies del gato. To make things a little bit more complicated. You don't have to use that because you already use the monotonic array. So we can do like all the things can be identified while you're doing the monotonic array. Yeah, okay, that's it. And you know what? I don't have Ghana today to handle this, so I'll just leave it maybe for tomorrow. All right, I'll see you guys tomorrow. Adios.